Okay, then welcome everyone to today's installment of the DutchCATS online seminar. So it's a seminar where we listen to talks about type theory and category theory and the relationship between the two, or maybe one of the topics. And I'm very happy that today's speaker is Norihiro Yamada, and he is going to talk about type theory and commuting conversions, I think.
Yeah.
But I don't see it. I don't see the slides yet, so I'm not entirely sure anymore what the precise title was. So, but we have had him before, and I think yeah, it was a very clear presentation. So he set this bar very high for himself. So, and I have high expectations for this talk as well. So take it away, please.
Thanks so much for the introduction, Benno. And I'm Norihiro Yamada, working on type theory, category theory, and game semantics at the University of Minnesota. And today I'd like to talk about my recent work on Curry-Howard isomorphism without commuting conversion. And let me first share the slide here, right? Yeah, I will. So wait seconds. My slides and can everybody see my slides? Cool. Including pointers. Good. Okay. Thank you. Okay. Thank you so much for this opportunity to talk about this work. And I think talk is more appropriate for explaining motivation ideas, especially for syntax. And so today I like to focus on main ideas and leaving the technical details to the paper. And my aim is after this talk, if you're interested, then you are basically ready to read the paper. And so let me begin with some background and motivation. Let me first briefly introduce Curry-Howard isomorphisms. And here I just display the implication fragment of the simply typed lambda calculus. So we have axiom and introduction or lambda abstraction and function application. And if you just forget terms and variables, then what you get is basically the implication fragment of natural deduction. And here I just for clarity display in sequent form. And this correspondence between lambda calculus and natural deduction is not only for implication fragment. One can do the same thing for product, coproduct, and even like a polymorphic lambda calculus or dependent lambda calculus. So such a general correspondence is something called Curry-Howard isomorphisms. This is correspondence between formal systems and type theories, in which formulas correspond to types and proofs correspond to terms. And moreover, proof normalization or cut elimination correspond to reduction. And one can exploit this correspondence so that type theories regarded as both logic and computation. So the idea is type theory can have an operation semantics regarded as programming languages, but also this can be seen as a format system. And one may wonder why it's important. Well, one possible answer could be that proofs and proof normalization are now formal objects in type theories, while in traditional proof theory, they are like a meta-theoretic notion. So in type theory, one can reason about this concept formally. And this particularly is convenient or useful to reason about equality. And equality of proofs is very important if you have like a, for instance, category theoretic point of view. Okay. So next, I want to introduce the concept of bureaucracy of syntax. So bureaucracy of syntax is loosely speaking about essential details in syntax. This term is coined by Girard. So this problem is maybe best visible in secant calculus. For instance, in the intuitionistic secant calculus, we have the following derivation tree. So right rule on conjunction, followed by cut. And another derivation tree is with the same assumptions. Then we first apply cut on both sides, then apply right rule on conjunction. So because proofs in secant calculus are derivation trees, so they are different derivation trees on the same conclusion. However, intuitively, what these derivation trees do looks like that's the same thing, because right-hand side is just constructed by right rule, the same rule, and cut is applied through formula A in this tree as well as in this tree. So intuitively, they should represent the same proof, but they're essentially distinguished in secant calculus. And this problem is coined by bureaucracy of syntax. On the other hand, natural deduction and simple tabular calculus is much more satisfactory in this respect, because the corresponding Raman calculus derivation corresponding to this secant calculus derivation is this one. So first, we apply introduction rule on conjunction on both assumption, and we get pairing. And then cut here is translated into meta notation, a meta concept substitution here. And we just substitute this hypothesis to this one, and we get this term. And here, A is substituted for X in this pairing. And by definition, this substitution is equal to, pairing of substitution. And on the other hand, this secant calculus derivation corresponds to this lambda calculus derivation. And again, we first translate cut into substitution, and we get this term. And this derivation is translated in this substitution. And finally, we just take a pairing. And one pleasing thing is that these terms just equal. So in other words, lambda calculus is more abstract representation of proofs than secant calculus. So in this sense, lambda calculus is natural deduction. Yes.
Just a quick question. Couldn't I claim that the bottom bottom sequent calculus proof is one step more cut free than the first one?
Sure. Yeah. Exactly. In a cut elimination procedure, translates this one into this one.
So I mean, in that sense, could I say that's the connection? I mean, that's why they're not. Could that be I won't say an essential detail, but a sort of computational difference between the two? Or that
sure.
Sound...
Yeah. And they should be identical if you take an equivalence class modulo cut elimination. So there, you can say that they are kind of computational different. Yes.
Okay.
Thank you.
Thanks.
Yeah. Okay. So So my point is, but without a computation, simple type lambda calculus is more abstract than secant calculus. But even lambda calculus is bound by bureaucracy of syntax as soon as you consider coproduct. So for instance, let's take this simple derivation in simple type lambda calculus on disjunction. We first take a, there is a spider on my desk. Wait a minute. Okay. Hopefully this is gone. All right. Sorry for distraction. So here we first apply introduction rule on disjunction. So, and this is kind of injection, constructor for disjunction, and same here. And then we apply elimination rule on disjunction. So we get some like a standard, like a case construct. The intuition here is, this S is kind of case analysis on X and Y. It's kind of a case analysis composition. And we have another derivation. So first we apply elimination rule to these hypotheses, and then apply introduction rule. And by the same reason, they should represent the same proof, because the difference is just in essential order of applying rules, but the resulting lambda terms are rather different. So for coproducts, even simply type lambda calculus, oh sorry, I should have lambda here. Simply type lambda calculus is not free from bureaucracy of syntax, and that's a problem. And for this problem, lambda calculus is usually equipped with something called commuting conversions, namely reductions between these in essentially different times. But they are problematic because, first of all, commuting conversions are often quite complex or tangled, and they are much more complex if you think of classical or linear lambda calculus. And they are very hard to handle. And more fundamentally, commuting conversions do not solve the bureaucracy of syntax in any essential way, because they merely take equivalence class of terms. So we still have in essential details in syntax, and we just merely take equivalence classes, which is not computationally significant. So my first problem is this commuting conversion in lambda calculus. I want to, in other words, I want a simpler, more abstract representation proofs. And second problem is classical and linear lambda calculus. So first, a brief motivation for this calculus. So first of all, classical lambda calculus extend logic and computation to classical logic. And for mathematical logicians who are interested in constructive foundation mathematics, this is appealing because classical logic is a standard foundation mathematics. And so one wants to have classical logic in a computational form. And also, this is interesting for computer scientists who are interested in like a principled programming paradigm. And then, classical reasoning coming from logic will be very kind of principled, powerful paradigm in programming. On the other hand, linear lambda calculus are kind of refinement of logic and computation, because linear logic refines classical intuitionistic logics by like reducing construct into more primitive ones in linear logic. On the other hand, classical lambda calculus are usually very complex and indirect. For instance, the famous one is lambda mu calculus, but usually a computation of mu variables much more complex, and also like activate, passivate operation mu variables. I feel a bit kind of indirect nature, at least than usual lambda calculus. And for linear lambda calculus, even intuitionistic one is already problematic. So initial attempts lack the basic properties such as closure and substitution. And after many trial and errors, several solutions have been established. However, classical linear lambda calculus, namely, so lambda calculus for classical linear logic is very hard to establish. And as far as I know, I think still no like a syntactic category of like a linear logic has not been established yet. I think, for instance, the first proposal by CD is not even sound categorical semantics, and people are working on a proofnet, but proofnets have not been extended to full classical linear logic. So yeah, term calculus for classical linear logic is a very challenging topic. And finally, another problem is lack of uniformity in lambda calculus. So let me first note that secant calculus offer a uniform format for the logics, and because then you can just restrict, restrict, for instance, the number of formulas on the right-hand side to be at most one, then you get intuitive logic, and you further get apply structural restriction, then you get linear logics, and so on. On the other hand, there is not such uniformity in lambda calculus. And for instance, you need new variables for classical lambda calculus, or like you have like a dual context for linear lambda calculus. So lambda calculus looks a bit ad hoc because each lambda calculus has its own kind of format. Therefore, a second problem is the complexity and lack of uniformity in classical and linear lambda calculus. And these problems I want to tackle in this talk. And motivated in this way, my main result is some simple type theories called sigma calculus. And here sigma signifies S coming from symmetricity, because in some sense, my calculus are symmetric for classical intuitionistic and linear logics that achieve, first of all, abstraction in a sense that there is no commuting conversion. And second, simplicity and directness. For instance, there is no lambda variable or dual context. And they enjoy basic properties such as closure under substitution, subset reduction, conference, and strong normalization. And finally, a uniform format, just like secant calculus, so that we can systematically embody classical, intuitionistic, and linear logics. And yeah, as I said, proofnets are very nice abstract representation proofs, but I think they hadn't been extended to through classical linear logic. Okay, so, and some of the consequences of this result is that first, I think this advances the theory of equality of proofs, because as I said, type theoretic equality, definition of equality on linear logic is pretty problematic. And this is also already hard in classical logic. So this is my result is a kind of nice language to define syntactically equality between proofs in classical and linear logic. And the uniformity of my type theory gives us a kind of systematic comparison between these logics, especially in the computational aspect. Finally, I find some interesting application category theory, namely some coherence theorem. Okay, so in the rest of this talk, I want to develop in a step-by-step fashion how I like okay, I arrive at my type theory in a step-by-step fashion. Okay, so the starting point is that because second calculi have a kind of uniform format, so initial idea is just introduce type theory that precisely mimic secant calculus. So the first format is the following. So we have the usual turnstile here, but also we have another dual turnstile here. And left construct, so capital A's are formulas and small p's are kind of inhabitants. And these inhabitants correspond to left rules in secant calculi. And construct on right hand side correspond to right rules. And construct in the middle correspond to CATS. And one remark here is that this term is symmetric or two-sided because left constructs can be non-variables. So this is a crucial difference from lambda calculus because lambda calculus only have variables here. And in the literature, this kind of syntax, namely allowing more than one occurrences on the right-hand side, exists in the literature, like lambda mu mu calculus by Curie and Haberlin, and some extension by Wadler. However, they all have only variables here. So in this respect, mine is different from theirs. And for convenience, we just abbreviate this syntax into this, where delta collects all p's here, and capital delta collects a's here, and small phi collects small b's, and big phi collects big b's, and finally pi collects all cuts in the middle. Just as a convenient abbreviation. And in addition to the uniformity, another advantage of these two-sided terms, that which is free from bureaucracy. So indeed, the two-sided terms solve the bureaucracy of secant calculi as well as the simplicity of lambda calculus. So let's revisit the problem of lambda calculus on coproduct, but now translate it into my syntax. So here is the assumption, and we apply right rule on disjunction. So this is just an injection. And then left rule, and we just apply left rule here. So this is possible, only possible because we allow non-variable on the left-hand side. And then we apply cut on this E and this P disjunct Q, and we get this syntax. And another is first apply left rule here, and then apply cut, and then finally apply right rule here. But as a result, we have exactly the same term. So in this way, we have overcome the problem of bureaucracy of simplified lambda calculus. And the point is, first of all, as in lambda calculus, we abstract derivation trees to terms. And secondly, we allow non-variables on the left-hand side as well as cut construct in the middle. That avoids kind of overlapping of constructs happening in lambda calculus. So in this way, my two-sided terms are very good abstraction of proofs. But then there is a problem to handle because left-hand side not necessarily variables, so we cannot share variables. What I mean here is, for instance, in the simplified lambda calculus, the introduction rule on conjunction, for instance, works thanks to the sharing of the same variables here. Because they have the same variables, we can simply have the same variable here. However, this is no longer available in my syntax because they can be non-variables. So we can no longer share here. And a solution is a superposition of side construct based on slicing due to Girard. So roughly, the corresponding intuitionistic schema calculus has a corresponding rule. So we have left assumption, right assumption, and point is delta prime and pi prime can be just very different from delta and pi. Now first, the idea of superposition is make conjunction to be unary operation. So unary on A here and unary on B here. And then we attach identifiers or numerals. And then we attach the same number at the tag. So I on the left assumption. So I on delta, pi, and j to delta prime and pi prime. And this is necessary because if you think of reduction, then if you apply cut on this term, and another is like a projection. And if projection picks left-hand side, for instance, then we have to keep all things with tagging I, so delta, pi, and then we should discard all, j, so like a delta prime and pi prime. So in other words, I and j gives kind of tagging position union and identify which construct to be deleted and which construct to be remained.
Sorry.
Yeah.
Yeah, so I'm not entirely sure I understand your notation. So, so I mean, okay. I mean, I suppose what is on the left and the right of this turns down, the turns over, is flipped around, are just like lists, for instance. I mean, they are lists, I suppose, right?
Which is which, sorry?
Well, these things that you have, like delta of type capital delta, they are lists, I suppose, right?
Yeah.
So is the idea? I mean, what is it? How do I read these curly brackets? Is it
I know.
I mean, for instance, if there are n elements in delta, there are still n elements in the list hasn't grown in size, I guess.
Yeah. What? So this is very like informal and rough notation.
Okay.
And for instance, here, tagging I is pointwise. So this I is each element in delta because delta is sequence, as you say.
Okay.
And this bracket is actually also pointwise. So each first component of delta and delta prime is paired.
Okay.
And then, so this is actually a finite sequence of pairs.
Okay.
Yeah.
And these curly brackets is some additional part of the syntax.
Yeah. But yes. I actually discard this like a informal syntax more systematically. So,
okay.
I know this is confusing. Yeah.
All right.
Yeah. Okay. So actually, your question is a very good introduction to the next slide. Thanks for the contribution. And yeah, so to implement superposition more systematically, we generalize our old format into a bit more general one, where now the curly P's and curly B's are finite merge set of all small P's and B's in the old format and equipped with finite set of numerals. So each element of Kali P's and B's, small P's and B's equipped with some finite set S and P coming from these I's and J's. If you repeatedly apply rules, then these I's and J's can be more than one. So this tagging can be a finite set of numerals. And just a small remark is that each element is actually can have some index. So maybe something like, like in this case and in this case. So what I'm talking about is some of the P's and B's may have these indices I and J. And finally, these sigmas in honor of the name of sigma calculus, just abbreviation of CAT construct equipped with the same set of numerals, because we have also numerals in the middle. Sorry. Yeah, and again, now the inside CAT we have finite math set rather than a singleton element like P's and B's. And just abusive notation, let me stick to this meta notation just for convenience. And now the old example is now more systematic without curly bracket. So given these two assumptions, we apply this construct to A and this construct into B. But this is a kind of point-wise operation. So this is a math set whose elements in A and this formal operation attached. And same for here. And we finally take disjoint union of the two. So this is a kind of another math set. And this, so because delta is a finite sequence, so we first apply. So so this notation is just to add I to existing finite set, something like S, and similarly for J plus J, and point wisely. And this disjoint union is again point wisely. So namely, take disjoint union for each like a first element of delta and delta prime, and second and disjoint union on second element of delta and delta prime, and so on. So as a result, this is a finite sequence of math set. So in this way, so this general format makes things more like a general and systematic. Okay. Then another advantage of so originally I introduced this generalized format to handle conjunction or disjunction, but this has additional benefit, namely it gives us explicit structural rules without commuting conversion. So let's think of left structural rules, for instance, and let me write this one for inhabitant for left weakening, and this notation for left construction. But now we can just define simply this construct to be empty math set, and this construct to be just disjoint union. And a praising feature is that this construct satisfies the desired equation, such as strict commutativity, because this is just a disjoint union, and weakening is just a unit, because this is just again disjoint union, and strict associativity. These rules are required by categorical semantics, and without relying on commuting conversion. If these constructs were just formal syntax, then these equations should be satisfied maybe by importing additional commuting conversion. But in my syntax, they are just automatically, they just automatically hold. without commuting conversion. So this addresses the main topic of this talk, namely pure accuracy of syntax and commutativity, so commutative conversion. And yet another advantage of the new format is the equality on units holds without commuting conversion. So let me write additive unit 1, 0 in a linear sigma calculus. Let me remark here that traditionally additive unit is written by top rather than 1, but categorically they must be terminal object. So I prefer instead write 1 for additive unit. And let me just write O and zeta for anonymous inhabitants for 1 and 0. And it seems natural to have O empty match set for other constants. And then for instance, we have the foreign derivation tree to apply this rule into this simple sequence. So namely, we don't have any delta or phi. And then we apply left weakening to get this empty match set. And one more again. So we got now 2 empty match sets. Then we apply control action. And control action just take disjoint union. And disjoint union of empty set, again, just this empty set. So what we get here is this one. But this one is simply you can obtain just by applying this rule. And similarly, if you begin with applying this rule, and you get this one, and you get a control action on right, and then apply weakening on right. But again, this is just what you can obtain just applying this rule, just all at once. So my conclusion is these derivation trees just generate the same terms as those given by the singleton application of this rule. So this illustrates kind of universal property of these rules. And again, without relying on commuting conversions. So this example illustrates the kind of abstract nature of this idea, this formulation. Okay, next thing to consider is a reduction. And for instance, it seems sensible to define reduction on conjunction, as I said. So these constructs are coming from the previous slides, the construction on conjunction. And now we apply cut on that with some, some left rule on conjunction. So we have projection here. And this projection is first one. So it picks the left-hand side. That means we should keep all i's, so delta, pi, and phi. And we should discard all delta prime, pi prime, and phi prime. So this must be reduced to this term. And this is exactly just left hypothesis of the construction. And similarly, if this is the second projection, then we should keep delta prime, pi prime, and phi prime, and discard others. So this becomes the second hypothesis. So this marks the kind of universal property of conjunction product. So this seems to be working, and for most other constructors. And here, just for abbreviation, we omit formulas and write comma instead of plus position union. And you can see here, the tags play a crucial role because they identify the construct to be eliminated. On the other hand, a problem is how to reduce cut inhabited by these structural rules. For instance, what if inside cut, this is empty set? it is not very clear how to implement this reduction, or you have decision union. And the point is, we cannot use standard cut elimination algorithm for second calculus because now we are working on terms, not derivation trees. So our reduction cannot depend on derivation trees. So we need something else. And to attack this problem, I got some idea from the notion of sequentiality. So what I mean by sequentiality is, for instance, we get the following derivation in intuitionistic sigma calculus. But first of all, we get left rule on bottom, and we write beta for anonymous inhabitant for bottom. And next we apply right rule on bottom, so we get this one. And we have another instance of left rule on bottom. Then we apply left rule on implication. And out of this beta and this beta, we get this inhabitant on implication from bottom to bottom. And then we can repeat this process to get finite copies of this construct of implication between bottom. And by sequentiality, I mean roughly kind of a computation in which only one computational step occurs at a time. And this can be formalized by sequential game semantics. And very roughly speaking, in such a sequential game semantics, every computation occurs first on the right-hand side, and then next step occurs some formula occurrence. So in this case, start with this one, and next step occurs in this beta. But now we have exactly the same copies of the same construct. So after starting on the right-hand side, it is unclear which construct to visit next. And syntactically, we don't have any information which construct to visit because they are exactly the same. So in other words, my syntax currently loses sequentiality. And you can see this problem in another example. So again, we get these terms, and we apply right rule on tensor, which we can probably write something like this. So this construct becomes this beta and this beta on the left, and this construct becomes this beta and this beta on right. And intuition is first, again, starting on the right-hand side, the computational environment or oracle picks left or right-hand side of tensor. And if oracle say picks this beta, then because this rule coming from this left assumption, so namely, so this beta connected to this beta on the left-hand side. The next step will be from here to here. And similarly, if oracle picks this beta, then computation will be here from here to here. But then you can apply exchange rule on the left-hand side, and you can switch these two betas. But syntactically, they do nothing because they are identical betas. So semantically, this corresponds to now like a flipping. So from left beta to right beta, and from right beta to left beta. But this kind of information is lost in this syntax. And same problem occurs in CAT. Suppose on the left hypothesis, the computation occurs from right-hand side to say delta. And similarly, suppose that computation occurs from right-hand side to gamma. But then in this resulting syntax, the computation from right-hand side, then the question is, the next is occurring in delta or gamma. We don't know which hypothesis to use. So in this way, sequentiality is lost in cut rule as well. So the conclusion is some rules are currently not preserving sequentiality. And that's a priori. Sorry, that's another observation. Okay, then let me briefly talk about other line of research. So meanwhile, I have established sequential game semantics. That is a kind of a mathematical formalization of sequential computation that uniformly embodies classical, intuitionistic, and linear logics. And this is obtained basically extending existing game semantics for intuitionistic and intuitionistic linear logic to classical ones. And this game semantics is also categorical. So the picture is, while we are kind of struggling to define syntactic formulation of logics, we already get a nice semantic formulation of the logics. So, and syntax has lost sequentiality. So my kind of intuition is that if we restrict rules and design reductions in syntax in such a way that precisely match sequential game semantics, then we may solve the problem I just mentioned. So I implement this idea by, namely, any construct with tag I can be visited only after visiting some other construct with index I. So let's revisit the examples. So first of all, this is the same thing as in a previous slide. How we do the sequentiality currently. But now we attach the tagging here. So constructs on left row, and I tag I to all constructs on the left hypothesis. So I come to here and also here. And if I repeat this process, then we get something here. And now, you have additional information on tagging. So if we implement the idea in the previous slide, this one, apply to this example, then again, computation occurs on the right-hand side. Then because this beta and this lambda has tagging, so we cannot visit them yet. So what we can visit is only this one. And this one has J. So this enables to visit next this construct having J tagging. And because this construct have index I, then finally, this means we have visited I and J. So we can now safely visit this construct finally. So by this tagging, this principle applied, we just keep a sequential information. And so namely, the only choice is visit 1, 2, and 3. And similarly, in the second example, we have tagging here. So this beta and this beta, and this beta and this beta is connected. And this remains kept if we exchange like a permute these betas. So again, we preserve sequentiality. And finally, cut. So we have I here, and this I is tagged on all left components. So delta, pi, and phi. And this means that before visiting cut, we cannot visit delta, pi, or phi. So this means after a starting point here, what we can do is first simulate right-hand side computation. Maybe stay in phi, stay in psi, gamma, or sigma. And at some point, this computation may visit P. this means visiting cat here. And this enables that because now we are visiting I, so this enables to follow left-hand side as well. So now through from P to A, the now control is given to the left-hand side. So yeah, sorry, I can't give you a detail here, but roughly in this way, tagging also preserves sequentiality on the operation cut. So my point is, this idea of tagging originally coming from superposition, but now this is also very effective to preserve sequentiality, so that my syntax is much closer to sequential game semantics, which has a nice categorical equation. And it further defines reduction in a pleasing way. So if we think of the previous example, cut, in which we have empty here, but then because now we have I connected to these tags, so it seems natural. So it seems natural to just delete these delta, pi, and phi with I, replacing with them with empty. So we have just empty on delta, and we just delete all pi here, and we just delete and replace all phi by empty. And similarly, for this kind of disjunction inside cut, what we need is just duplicate this construct with I twice, but with a fresh variable. So I just change I with J. In this way, we can implement reduction on structural rules. Here, this one is abbreviation with this one. So again, pi is duplicated, and cut is also split, and so on. Let me skip this point. I'm just talking about the other case. So when A is empty or A is disunion, it's slightly trickier. But let me skip this point in this talk. Okay, so I just introduced the key ideas, and at the end I have concrete typing rules to show you. But before that, let me conclude this talk and talking about some future work. So by implementing these ideas, I have established type theories for the sigma calculi for classical intuitionistic and linear logics equipped with reductions. And they enjoy basic properties such as closure under substitution, subject reduction, conference, and normalization. And they enjoy uniform format like sequence calculi, but it is possible to compare directly between the computational aspects of the logics. And crucially, there is no commuting conversion. So addressing the main theme of this talk, this enables a simple and abstract representation proofs by times. And by sequentiality, there is rather direct correspondence with game semantics. So game semantics, from game semantics, we can just extract a canonical formal language, which is also programming language, namely sigma calculi. And future work, first of all, by this work, now term equality is much easier to handle. So, and I'm going to complete the corresponding categorical semantics. And hopefully we can get sound, complete, and internal language theorem. And also, I find that mutual translation between them is possible. And they are much simpler than existing CPS translation. And I believe that there is a categorical counterpart of this translation. And also, this framework seems appropriate to to compare call by name and call by value distinction. And as Selin just said, they are kind of dual. So I want to analyze this distinction in a framework of signal calculus. And finally, hopefully, I can lift signal calculus to dependent type theories so that we can get dependent type theory with classical and linear computation. Okay, then let me just quickly go through some of the typing rules here. So as I said, okay, so what I'm displaying here is just linear sigma calculus. And here, so weakening, we have just an empty math set, and contraction is just given by vision union, and direction is just by this simple construct. And again, the point is we allow non-variables on the left-hand side, and yeah, the same for the other rules. And cut is just as I displayed the additional index here. And here is an axiom. And as I said, yeah, unit rules for additive. And yeah, unit rules are kind of just we attach like a beta, as I said. And this is a left rule on tensor, which is unary. And as I said, for right rule on tensor, we attach I and j, and corresponding I on the left-hand side, j on the right-hand side, and dually on par. And yeah, the left rule on additive conjunction is projection on the left-hand side. And right rule is I just already displayed in a talk. We just take a unary operation on the left-hand side and another unary operation on the right-hand side, and the corresponding tagging here, and dually on product. Yeah, and let me skip an implication, but in a similar way we can just formulate. Yeah, so let me stop here, and thank you so much for your attention.
Yeah, okay, thank you.
Thank you.
Little pause.
Thank you.
Nori. All right. This gives us some food for thought, I think. So are there some questions? Maybe people can just, if they have a question, they can just unmute themselves. Otherwise, I have a few questions as well.
Mm-hmm.
So yeah, so one thing which confused me is maybe it has to do also with the motivation. So I mean, in a way, you could say that how to say? I mean, of course, there is. I mean, like normalization and cut eliminate. I mean, if you rewrite a proof or a lambda term or a sequent calculus proof using cut elimination or normalization, you could always say, I mean, the intuition that people often have is that, I mean, when you do one of these reduction steps, I mean, the thing that, yeah, you rewrite something into something else, but it is essentially the same proof.
Yeah.
So if you, I mean, you could argue then that maybe if you had a representation of, I don't know, maybe the type lambda calculus, which is free of any bureaucracy of syntax, there should be no reduction anymore, because you only write down terms which are just in normal form, and any form, I mean, not just the commuting conversions are gone, but any conversion is gone, right? So that would be a fully abstract representation of I don't know, the type lambda calculus, or I mean, whatever. But that's not what you're saying. I mean, there's, in particular, there's still a notion of reduction in your work. So why, yeah, so where do you, what is still bureaucracy of syntax, and what is?
Sure.
Yeah.
So, okay, so first of all, I definitely want to preserve beta reduction because it's computationally significant.
Okay.
Yeah. So, but commuting conversions is significant from the at least computational point of view. And so ideally, we just want beta reduction and eta reduction, eta expansion.
Yeah.
But then nothing else.
No, okay.
That's first, yeah. And another thing is, so as I said in the talk, commuting conversions are in general very, very complex and hard to handle in comparison with beta or eta reduction. So if you really want to apply like a category theoretic analysis on type theory, usually you definitely want to eliminate all commuting conversion.
Okay.
That's the kind of motivation behind this work.
Okay. So,
I strongly recommend to have a brief look at Gavin Bierman's PhD thesis talking about intuitionist linear logic. And there are great Gavin Bierman.
Okay.
Where can I write? I can write the name later, but
okay.
In his thesis, there are crazy number of commuting conversions, like 100, 200, and I imagine nobody wants to work on that kind of syntax.
Right. So you imagine. I mean, so you imagine that to have in this categorical semantics that you have, you would. So beta equal terms will not be necessarily identified, but things which sort of differ up to some sort of by a commuting conversion will be identified. That is the idea. Or
in my work?
Yeah.
In my work, simply what can I say? So commuting conversion simply do not exist. And computation happening only in beta and eta reduction.
Yeah, okay.
And yeah, as I say in the literature, I think mainly due to this complexity, I've never seen like a completeness, let alone internal language theorem for classical linear logic. And I believe that this is due to this problem. Yeah.
I see. So So yeah, so you mean also in the sort of the slide where you mentioned future work. You mentioned the categorical semantics / the internal language. So can you give us already a hint of what the categorical semantics is going to be? Or
yeah. So definitely not a autonomous category because this is based on game semantics, and game semantics doesn't have, it has, but it's polarized, I would say. Okay, roughly speaking, the category semantics is different from the traditional categorical semantics of classical linear logic, which is a star autonomous category, but rather I start from categorical semantics of intuitionistic linear logic,
Okay.
which is some sort of symmetric monad cross category with some co-monad. And I
Okay.
just have a dual structure. So another tensor for par, and instead of co-monad, monad for final. But it's kind of restricted to a certain fragment, because if you have both, then it just collapses to Boolean category. So this is pretty much similar to Selinger's control category. In control categories, you have products, but you don't have a perfect coproduct. Coproduct is restricted to some subcategory.
Okay.
So that's a kind of rough picture of my categorical semantics.
Okay.
And,
Okay.
Yeah.
Yeah. Okay. I see. And and it gives you a categorical semantics sort of like for full classical linear logic is the idea as well.
Yeah. Yeah.
Yeah. Okay. Okay. Let me see. Yeah. So the other question I had, I mean, maybe the final question I had is I mean, was you mentioned this sequential game semantics as
Yeah.
I think.
Yeah.
I mean, the feeling I got when you were talking about it, it was like maybe it was actually an important source of inspiration for the things that you've been doing.
Yeah.
So I mean, is it possible? I mean, I don't know. I could just imagine. I mean, maybe you even said that at something point, but I think you could maybe even take that as a starting point for your work, or present it as like a syntax maybe for sequential game semantics or something like that. Is that right? Or I mean,
Yeah. So the inspiration idea actually coming first from game semantics.
right.
And so pretty much I kind of syntactically implement that
Right.
one. And
Okay.
I know on the one hand, syntax is very difficult to handle this problem, but on the other hand, we already have nice semantics. So one good strategy seemed to me that to being guided by semantics.
Right. No, I like that strategy. Yeah. Okay. Yeah. Right. Yeah. Yeah. I mean, for me, I think also personally, if I see the categorical semantics, or maybe I see what you mean by this sort of sequential game semantics, then it yeah, I don't know. It gives me maybe even a better feel for where the syntax comes from and why it looks the way it looks. Yeah.
Thank you. Yeah, I'm also writing up to make precise the correspondence between game semantics and the syntax.
Right.
And the point is, if you're used to the notation, the things are not only inductively defined, but you can see the direct correspondence. So, namely, once you're given a strategy in game semantics, you can canonically read off directly from strategies what the corresponding term, non-inductively. And so such that correspondence, I think, I'll give you a more intuition about this.
Yeah. Yeah. No, I would imagine. All right. Okay, these were my questions. Are there other comments, questions, remarks? No? In that case, let's thank Nori again.
Thanks so much.
And yeah, maybe you could